Hello everybody, thank you for joining me once again at the very end of this 2005 Cayley contest. So we'll be wrapping up the 2005 grade 10 multiple choice Cayley competition from Waterloo in this video, question 25. If you're interested in more Waterloo contests, you can of course click the second link in the description. It'll take you to all their past contests. And the next sort of multiple choice contest I'll be going through is the 11th grade level Fairmat. And of course there are written competitions, most notably the Euclid, but there's a grade 10 written competition, the Galois, and that will be up soon as well. And if you found this one a little too hard, might I suggest trying some of the easier contests, the Gausses, Pascal's grade 9, and if you're looking for a grade 9 written, of course, the Friar. But that's enough of that, let's get to it. Question 25, the very last one. The positive integers a, b, and c satisfy 1 over a squared plus 1 over b squared equals 1 over c squared. The sum of all possible values of a, which is less than or equal to 100, is... So I have a bunch of options. I'm noting that 3 of them are in the 600s, so I would be thinking that we're able to get at least 600 most likely, just because 3 out of the 5 are over 600. But I could be surprised. Maybe it's 555. Maybe it's 315. Who knows? Well, we will as soon as we figure out how to do this question. Now, 1 over a squared, 1 over b squared, 1 over c squared. This puts me in mind of Pythagorean triples, just because I've got squares plus squares equals squares. But if a, b, and c are positive integers, these aren't squares. Well, I mean, they are. This is 1 over a all squared. This is 1 over b all squared equals the fraction 1 over c squared. But I'm thinking things like Pythagorean triples, so like 3, 4, 5 triangles, and that requires integers. Integer squared plus integer squared equals integer squared. So I ask myself, is there a way to sort of turn these guys into Pythagorean triples? And there is. If we multiply through by a squared, b squared, c squared, we can turn this statement into one involving some squares. So let's take a look. So we know 1 over a squared plus 1 over b squared equals 1 over c squared. I'm just going to multiply everything by a squared, b squared, c squared. So we're going to get a squared, b squared, c squared over a squared plus a squared, b squared, c squared over b squared equals a squared, b squared, c squared over c squared. And some of these guys happen to cancel out. So the a squareds, the b squareds, and the c squareds. And now what are we left with? Well, we're left with bc all squared plus ac all squared is equal to ab all squared. But because a, b, and c are integers, positive integers, so will bc, ac, and ab. So we just need a Pythagorean triple that works like this, right? Well, I don't think quite exactly, because, look, if we were to say, okay, 3 squared plus 4 squared is equal to 5 squared, that's absolutely true. And so then what would we need? We'd need 3 is BC, 4 is AC, and 5 is AB. Okay, how do we solve this? Because we don't want the values for BC. We are specifically asked, we want the sum of all values of A, where A is less than or equal to 100. So we need to be able to isolate A in some manner. How can we solve for A? Well, we have a system here of symmetric equations. So A appears in 2 of them, B appears as a factor in 2 of them, C appears as a factor in 2 of them. So if I multiply all of these, I get 60 is A squared, B squared, C squared. Okay, so I could square root them. 60 is A, B, C. Now I'm noticing a problem right here. I'll get back to it. But my point is, if I want A, that's ABC over BC. And so that would be root 60 over 3, and I can solve for 3 there. Now, if you couldn't see the problem over here, we can see a problem pretty quickly here. Root 60 over 3, not an integer. Okay? If a, b, and c are integers, you'd expect a times b times c to be an integer, but root 60, not an integer. So we've got something going on. Not any Pythagorean triple will work here. There's probably only a few that will. And so part of this problem is narrowing those down. But solving for A in this way is exactly the sort of setup we want. We just sort of need to figure out what Pythagorean triples can go here. Because if A, B, and C are integers, these will have to be integers, and so you will be working with a Pythagorean triple. So it might be easier to say something like, let A be BC, B equal to AC, and C equal to AB. So then we're looking for Pythagorean triples, A squared plus B squared equals C squared. And if I want to solve for A is the square root of the product ABC all over capital A. Right? Because it would be A is BC, B is AC, and C is AB, and so ABC is the A squared, B squared, C squared. Yeah, okay. And then if we need it, although I don't know whether or not we will, we can also get the other ones, little c and little b as well. Okay. So what Pythagorean triples A, B, and C will work? That's sort of what we're left to figure out. If I have an A, B, and C and it works and it gives me integer A's and integer B's and integer C's, we're all set. But how can I ensure that little a, little b, and little c are integers? So we need integers. How can we... Because obviously 60 here didn't work. 60 became a problem. So I guess we need to ensure that ABC is a square. Now, is that the only thing we're going to need? So if A is root ABC, capital A has to be a positive integer because he's B times C. And he's part of a Pythagorean triple here. But, so we need ABC to be a square. Let's call it, I don't know, k squared. And then, so square root of ABC is k. We also need A to divide k. We need B to divide k. We need C to divide k. So, how do we make this happen? Not only that, I mean, we can say k is A times capital A. Just rearrange, because this guy here is k over A. And we get the other equations from the other side. I don't know how helpful this will be, but I feel like we're probably going in circles here, but we'll write down this equation. We don't know what we need yet. So we need A times B times C to be k squared. Now, obviously, 3, 4, 5 didn't work. 3 times 4 times 5, 15 times 4, 60. That didn't work. But it has a 4 in there, so 4 times 15. If we could just get some more 15s in here, I think we'd be all set. But we need to keep a Pythagorean triple. So I think if I do 3 times 15, 4 times 15, and 5 times 15, what do we have? We'll have 45, 60 in here, and we'll have 75. And if I multiply all those, I'll get 3 additional 15s in addition to the 15 we've got here and the 4 we've got here. So we'll have 4 times 15 to the 4th. So that's 2 times 225 all squared. So now we've got a square. K is 2 times 220. K is 450. So we were able to guarantee that we get a square just by multiplying what was left over here. And that will always work. Because we'll always have 3 triples, and so we'll get some square part, and then we'll have some other leftover stuff. And if we just multiply our AE, BE, and CE, then we'll still have our d squared, but we'll have e to the 4. So this will always work. The question is this all we need to make work? So let's work out our little a. So little a is 450 over capital A, which is 45. So great, he's 10. And I suspect so 450 over 60. So now we've got a problem. So the zeros cancel out. We get 45 over 6, which is 15 over 2. So we have to be a little careful. Just because a turned out to be an integer doesn't mean everything else will. And c, that's 450 over 75. The 25s will cancel out. We'll have 18 over 3. Yeah, because multiplied by 4. 4.5 times 4 is 18, so 18 over 3. So we'll get 6. Okay. So we're a lot closer than we were. Okay, no root 60s left. But our little b is a fraction. Now, I'm considering that progress because it's not irrational anymore. It's clearly a ratio. So I think if we multiplied by a little something more than 15, like, well, not 30, because 30 would leave extra powers of 2, extra factors of 2, but something, maybe multiplying by 60. Maybe we just need to take a Pythagorean triple like 3, 4, 5, or 5, 12, 13, multiply those all together, and then that's what we scale it by. I don't know, but this is what I'm just thinking out loud here. So we need to have little a, little b, and little c be positive integers, because that's the condition we started with. So how can I guarantee that? It seems like we need to have some sort of relationship with the big A and the little k. Because here the problem was B didn't divide little k. And why didn't it divide little k? So the 10 was fine, the 3, there was just sort of an extra factor of 2 down here. But k had a factor of 2, it just didn't have 2 factors of 2. And why is that? I think it's because 4 here was 2 squared, and there were no other factors of 2 anywhere to contribute. So k squared got 2 factors of 2. We square rooted, k only had 1 left, but our capital B still had factors. It had a sort of a square kicking around in it. So that was sort of the issue. So I want to say something like if P is a prime and it divides A. Actually, no. If P is a prime and it divides A, then P divides ABC. So P squared divides ABC because that's a square. And so it's pretty clear that P divides K. But if P squared divides K, this train of logic doesn't follow through. So if we have a prime P, P squared divides capital A, we need to ensure that P squared divides K. D squared divides A, because that was sort of the issue. It wasn't that there was a 2, it was that we needed 4. 4 was the square, so he sort of... So 4 squared, if D squared divides A, so now we're just talking about any common divisor, or any divisor here. Then D squared divides ABC. So D squared divides K squared. So I can tell you that D divides K, but I want to make sure that D squared divides K. Otherwise, we'd have a problem. We need D squared to divide K. So, what can we do? What are we to do? So I'm a little stuck here. I have a feeling that it's the Cayley. So this is probably a very quick, there's probably, we just pick some Pythagorean triples, start multiplying, and we could probably make a very simple chart here. And if you wanted to do that, or if you did do it, that's probably fine, because I can't imagine. It's a less than 100, and that kind of limits the triples. But I'm trying to better understand this and be able to say, no, these are the K's we need. This sort of thing is what's going on here. And so that's what I'm trying to work out here. Okay. And I'm a little stuck as to what it is. It's clear that if D divides A, then well, no, if D divides A, no, it's got to be for primes. P dividing A means that P divides K. But for something like P squared, well, suppose P squared divides A. Then P squared divides ABC, which is K squared. So we know P divides K. I suppose with a statement like this one here, I guess K kind of has to be a square, doesn't it? No, not entirely. Because they could have other things other than D squared kicking around. I'm wondering whether I give up trying to understand the theory and just try and make the chart like I suggested. But I really wanted sort of a complete understanding for 25, just so that I don't miss anything. Like, obviously, if I just make a list of a ton of Pythagorean triples, I can compute these K's and we're done. I thought maybe I could narrow it down a bit more. I think I'm too stuck. So what I'm going to do is I'm going to table this for a moment, and we're just going to solve the question. And if I think of something better while I solve it, I'll develop a general theory. But we don't need a general theory to solve question 25. That was just me trying to better understand what was going on to maybe narrow down the chart. But I am at a loss. I'm sure there's probably some argument with primes and something that we could narrow down the K's, but at this point, it's taking me too long, and you should never try and take too long with something. If you think you've got a way that works, go with it. So let's make some Pythagorean triples. So A, B, and C, and then what would be the K? And then A is K over capital A. B is K, because we're going to need to double check all of these. And C is K over capital C. And if all these last three columns are integers, we're all set. So we know with 3, 4, 5s it doesn't work. Let's try multiples, so like 3x, 4x, 5x. So k will be 60x squared, sorry, 60x cubed, or that's k squared. So it'll be 4x squared times 15x. And so that's k squared. So k would be 2x, and then we need 15x to be a square. And then k over a would be 2/3 root 15x. So we'd need this to be a multiple of 3 in there. Not an issue. We'd need this to be 1/2 15x. And this one over here would be 2/5 root 15x. So in order to, let's give myself a little bit of space towards the bottom. So root 15x, in order to be a square, we need 15 to divide x. And so 15 would be, so x would be something squared times 15. Okay, so when we do something squared times 15, we get 2 over 3 root 15, or root 15 squared times d. So we get 10d. And over here we get 15d over 2. So we need d to divide to be a multiple of 2. And over here we get 15 over 5, leaving 3, so we get 6d. So 2 needs to divide d, and then we'd be all set. So we could have x be 15 times 4, 15 times, so 16, so 15 times 16 would be 240. We could have 15 times 36, 540. All of these would work nicely. Okay. But, so then what d values work? So I'm not going to make the grand chart that I did. I'm probably going to have to make one chart per Pythagorean triple, per primitive Pythagorean triple. But if d is 2 or 4 or 6, a, b, and c, we get 20, 15, and 12. Okay. If it's 4, we get 40, 30, 24. If it's 6, we get 60, 45. Doesn't really matter what this one is, but 36. And we can keep going. Notice that A and B are interchangeable. So we can get the same sort of results if we did A is 4x and the B is 3x. So really we're making anything that A can be, or anything that little b can be, A can be as well. So if we had 8, we'd have 80, starting to get up there. Once we go d equals 10, we have 100, so we got a problem there. But we could still have b as 75. 60 in here would be fine. I don't really care what the c's are, because the only constraint is A has to be less than or equal to 100. 12, we'd have 120, but really we don't need this column anymore. That would be 90, and then the next one would be 105. So we have 15, 20, 30, 40, 45. We've got 60 twice. We're not going to double count it. 80, 75, and 90. So what's this total so far? I want to grab a calculator. 15 plus 20 plus 30 plus 40 plus 45 plus 60 plus 80 plus 75 plus 90. We have 455 already. Because the A's and B's are interchangeable. Okay, 455 already. What does that do? That rules out A, and it's not making 555 look any better. I mean, admittedly, if we found some more values of A that were less than 100, yeah, maybe, but the 600s are, again, looking quite nice. But we've generated some values. Great. So let's do this with another Pythagorean triple. So this worked. So it's actually a great thing that I stopped my little theory escapade. Okay, so what do we need? We'll get k squared, and then we need to square root it. So the next Pythagorean triple we should be working with is 5x, 12x, and 13x. So k squared will be 60 times 13. So 780x cubed. 780 as a square gives us, we've got 4. And that's really it. So we still have 4x squared here, and then we've got 195x. So k is going to be 2x root 195x. So 195 has to divide x, so let's let x be 195d. And so then this would be little a would be k over capital A, so that'd be 2/5 195d. Sorry, d squared. B would be, I don't care about C anymore, by the way. Well, I do care a little bit just to make sure he's an integer. So C would be 2 over 13, 195d. And then B would be 1/6, 195d. So the nice thing is we get divisions, 195 divisible by 5, so we get 2 times 39, so we get 78d for little a. We get 195 times 2 divided by 13. We get 30d for little c. And 195, sadly not divisible by 6, is divisible by 3. So we get 65d over 2. So once again, we need d to be even. This seems to be a recurring theme. So maybe if I hadn't been playing around with p's, maybe if I'd been playing around with 2's. Because it seems like 2 is the only problem every single time. So if d could be 2, 4, 6, 8. These numbers are much higher, so, I mean, really as soon as d is 2, a is out. But maybe some b values. So so don't care, that's too big. This will be 65, and the c will still be an integer. So 2 needs to divide d. That's what we learned there. And then the next one, 4 is going to be too big because we're going to have 130 here. So I guess we had sort of only one other extra value there. So we had 455, we'll add on 65, and so that'll be 520. So 520 is currently our tally, and if things keep slowing down, maybe 555 is the answer, but I would still bet right now on the lower 600s. Alright, just before I go on, Pythagorean triples that we need. So 7, 24, 25 is a great one. It's primitive. 8, 15 is 17 is one that people often forget. And then there's going to be things like there's something. There's 20, 21, and I think 29. I'm going to double check that one. Yep. I think the 9, 40, and 41, these are all great ones. But I'm starting to think that the numbers are going to get too big. So going back to theory just for a moment, if we're dealing with a primitive triple, so let's maybe let PQR be a primitive triple. Then we'll let A be PX, B be QX, and C be RX. Only one of these will have a factor of 2, and in fact, I believe it's got to have a factor of 4. Yeah, it's got to have a factor of 4 for what does it? I seem to recall there's a theorem that says one of these always has to have a 3 in it, the other one always has to, another one, possibly the same one in the case of 5, 12, 13, is a multiple of 4. So we'll always have a factor of 4 kicking around somewhere. And so as a result, I think the little d's at the end that I've been playing with will always have to be even. But k squared will be PQR x cubed. And so we'll need PQR x to be square rootable, and then x squared. So I don't think, other than a factor of 4, no, not other than a factor of 4, but I was going to say, I think there's only certain squares that can pop out from here. So 2 squared, certainly that's doable. But, yeah. So I think we're getting close with theory, but again, we're just going to have to sort of go to our charts. It's a shame, because I thought maybe we could sort of eliminate certain possibilities, like the 20, 21, 29. Do we really need to take a look at that? That's the idea. Well, there's a fantastic way that you can always write all Pythagorean triples. So for any, just because I want this theory done. So for any u and v, if it's a primitive triple, you can do p is u squared minus v squared, q is 2uv, and well, you need a factor k in there to make it all triples. So 2kuv, and then k u squared plus v squared. And so maybe if we stick that under here, so we'll get, oh, and I don't want this little k here. We'll make it s. No, we'll make it w. So for any w, u, v, and w, so k squared would be pqr, which would be w cubed times 2 times uv times u squared minus v squared times u squared plus v squared, but this is a difference of squares here at the end. So we get u to the 4 minus v to the 4. So does this help us? No, not really. Yeah, there's nothing I'm going to go. So we're just going to continue on with these triples and the charts that we've been doing. So if we had 7x, 24x, and 25x, and then let's do a bunch of them in terms of figuring out the k squareds and the little x's and the d's. So another one would be 8x, 15x, 17x, and we'll do one more right now. So 7 times 24 times 25, that's something. Sure is. 7 times 24 times 25, 4,200. So we can at least take out a factor of 10 there. 10 root 42x. How about 8 times 15 times 17? 2040. So that's got a factor of 4 in there. So we can take out a 2x and then a root 510x. That's not going to go well. And 9, 40, and 41. Well, I can already take out the factor of 4 there from the 40. And the 9 as well. So we'll get 6x. And then root 410x. So I suspect these two are going to be a little too big. So if we want a to be as small as possible, we're at least focusing on the b's. Because b's, I'm writing my b's as bigger than my capital A's. So little b in this case would be 10 over 24. The x's will cancel out, so we'll have 5 over 12 root 42x. And 42 will have to be a factor of x, and then we'll have 42, 5, 12. I think this might be too big. 5 times 42 divided by 12. 17.5. Okay, not ridiculous. So we'll put a d there. We can get 35d over 2. So that's for this one. So for 7, 24, 25, we have d. Our a will be 10. So we'll have 60d. And that'll be our little a. Our little b will be, as I said, 35 over 2d. I don't care about the little c. Well, do we care about the little c? So the we'll get 10 over 25. So yeah, we'll have 42d, where x here is 42d squared. But that'll be over 5, so we'll need d to divide. So we'll need 5 to divide d as well. So we need at least 10 here. So b here would be 35 times 5. That's too big. It's too big. So we're not going to get anything with 7, 24, and 25. How about 8, 15, and 17? So we get 1/4 510d, where x is 510d squared. So that would be our little a. Our little b would be 2/15 510d. And our little c would be 2/17 510d. Well, some of these can go away. For example, 510 has a factor of 15. So we get 34 times 2, we get 68d for b. Not so bad. Unless d happens to be a multiple of 2, which it would be because of a. Yeah, it seems like multiples of 2 are really, really destroying us here. So only one of PQR is a multiple of 4. And so k squared is going to be PQR x cubed. So we should only have one factor of this is going to be 4 times something. Let's call it y. So this is going to be 4x squared xy root x, or 4x squared xy, and then when we square root, we'll have 2x root xy, and then we'll need to in some way make this a square. But the point is we won't have any factors of 2 coming from the x's right off the bat. The only factors of 2 so far is this 4, which goes down to a 2. But let's say p has the factor of 4. When we divide by px, the x's go away, but there's an extra factor of 4. We might call him 4t. And so then we're left with 1 over 2t root xy. Now, since x doesn't generically have any factors of 2, because x could be 1, x could be 3, x could be... We're going to have to ensure 2 divides y. And then... what is it? So it's y has to divide x in general. Something to that effect. But we'll have to have 2 divides x. And what have we been doing? We've been saying let x be whatever's left over d squared. Whatever's left over when you take out all the squares from PQR, the 4 is gone, so there's not going to be no 2's here. So 2 will have to divide d. So as soon as I can get something like 68d, I know that has to at least be d being divisible by 2. So that's going to fail because of things like this little a having to be an integer, and it's a quarter 510d. So d has to be a multiple of 2 at least. So that does stuff. I think this is going to eliminate just about everything we've got, but we only have a sum of what? 455. The 65 there, and then all these ones here. And we need the sum of all possible values of a less than or equal. Okay, so we actually have an extra 100 here. So this is 555 is our sum now. But we added 65, so it's 520. So do we have a 620 or... What's going on here? So we do have a 620 here. Fantastic. The question is, can we get 680? So we'd need to be able to get a sum of at least 60, wouldn't we? Or sorry, yeah, we need to be able to sum up with some other a's being 60. And I think, frankly, we've just gone too far. I'm trying to think, is there anything we've seen so far? Because with these 7x, 24, 25, and everything, it seems like they're getting too big. Now, whether or not you want to prove that is entirely up to you. I want at least some argument in place that makes me think that that'll be the case, that we've gone too far. Because right now we have it narrowed down to 620 here, and the only other one is 680. So, I'm not one for just calling it quits without being able to prove that I can't go further. So I think I'm going to continue on a little bit. Is there a way I can make this divisibility by 4 stuff a little more concrete? So I know one of P, Q, and R has to be a multiple of 4. And only one. So that's the only sources of 4s. And this forces the d's to be, that I've been using, to at least be multiples of 2. So, provided that, so where did this 68 come from? So he was 510 over 15. Where did the 510 come from? Well, we took out the factor of 4 here. And should we even be taking out the factor? Because the 25 up here also messed us up and made d have to be... It looks like... Oh, we're still in blue for some reason. So if prime, I don't know what's a good name for a prime, f divides a, we'll make it our primitive triple, divides our little p. So, no, if a prime squared divides little p. Now, what do I want to say? If f squared divides p, then f squared can't divide q or r. Because otherwise, then it wouldn't be a primitive triple. Let's leave the primitive triple thing aside for a moment. If I have a prime, and I square it and it divides a, then either that prime squared divides b, and therefore that prime squared divides c, because, for example, c squared is a squared plus b squared. So if we have prime factors here, we'll have... so if a squared plus b squared is divisible by 7 squared, then c squared being equal to them must be divisible by 7 squared. Okay. So either have that's the case, or the prime squared doesn't divide b or c. And it's that case that seems to be causing our d's. So, I just want to show that we'll always get something like 50d or more. Well, 51d or more. Because everything's going to be even bigger. Because we get 68d here. And we need something equally as good over with the a, the little a here. It's got to be something with primes, but I don't want this video to drag on too long. I think we've got the answer, which is 620, because I think it's very unlikely we're going to get 60s. Anything 60 or less. Well, we can't add on another 60, so it would have to be a sum of some smaller things that gave us 60. So like, I don't know, 42 and 18 being possibilities, something like that. And while that's not outside of the realm of possibility, I feel like there's a way with primes to show that it won't work. So suppose we had a primitive triple. What we mean by that is if S is prime and S squared divides this product, and then S squared divides P, or S squared divides Q, or S squared divides R. And that's what we've seen. This also encapsulates the 5 squared problem. Okay. So let's write PQR as T squared plus some y, or times some y, and for all primes S squared does not divide y. So y is what's called square free. Okay. So then ABC is PQR x cubed, which is TX squared times YX. So K is TX root XY. Now Y is something given to us by PQR. And so we have little a is T over P, the x's cancel out, root XY. Little b is T over Q, root XY. And little c is T over R, root XY. Okay. Now, y has nothing. So in order for this to be square, which it must be, it's got to be k squared. We need to have y divides x. So let's let x be y d squared as we have been doing. So this gives us a is t y d over p. B is t y d over q. C is t y d over r. So PQR is t squared y. So we get so we can change a to be p over t PQR d, and now the p's cancel out. And then this t here, I don't think this is quite the way I want it to go. So whatever this y is, he seems to be a bit of the problem. So we know 2 divides t, because there's at least going to be a factor of 2 that pops out from the 4 from PQR. Okay. So let 4 be the one, p be the one that 4 divides. So 2 is a factor of t. Now there aren't going to be any other factors of t because it's PQR and it's a primitive thing. So any other factors of 2 must come from y, which it can't, or d. So then, so let's let p be 4u. Do I want to say that? No, I don't want to say that, but it follows pretty quickly that 2 needs to divide d. So, as long as ty over p or ty over q is less than 50, we'll be able to get more results. By the way, I think I'll try and finish this up. I might give up in a moment, but we certainly, I think, have answered the problem. I'm pretty sure it's E. So for those of you who want it, I'll even write E down right now. Because there's no way a Cayley question is going to go on this long. Unless I mean, it's entirely possible that I have just chosen the wrong approach, but I think we're okay. And so we need ty to be at least, or to be at most 50 if we're going to get more possibilities. Okay. In fact, it can't even be 50 because we already have counted 100 once, which I almost forgot to count. So, that means PQR, which is t squared y, can be no more than 50t. But look at the triples we've got. We've got 7, 24, 25. We've got 8, 15, 17, 9, 40, 41. And I mean, that's not even mentioning the extra d bits that make up the x. But what have we got for a product? Well, we had 8 times 15 times 17, 20, 40, and so that was so here t was 2 and y was 5, 10. ty was not less than 50. Oh, actually, no, because the part of the t could cancel out. So this over 2. So ty just needs to be less than or equal to 100. I don't think that'll matter. So here t was 10, and then we had 6 times 7, so y was 40. Yeah, so 420, I'm sorry, 4,200, way too big, way too big. And this one was 2040. So with this 9, 40, and 41, we had what? T was 2, no, T was 6, and Y was 410. Again, way too big, way too big. As soon as we reach the part where PQR is greater than 10,000, because at best T squared could be the whole thing. So I suppose we should keep writing out triples, primitive triples, until we get greater than 10,000 for the product. But, you know, that's a more solid theory than working out these T's and these Y's. So 11 times 60 times 61, we're already over 10,000. That's 4,260, and that's the next smallest primitive one, because the next one would be 10, but 10 isn't the one that has the factor of 4, so we're all set. We could even throw in something like 20, 21, and 29, but even that's going to be too big. Yeah, because that one's 12, 180. So I think that condition there forces us to say, yep, we got them all, and it is an answer of 620. I am certain that they did not intend us to actually prove. I imagine that they probably just wanted us to do the lists as I had been doing. But there we go. There is our full sort of solution. I guess I didn't go through all possible primitive triples PQR, but I think I've made enough headway to say, yep, as soon as it's bigger than 10,000, TY is going to be way too big. So there we go. There can be no more. And so the 620 that we added up, and that we added up a long time ago, although I did forget A could be equal to 100, so that took me a little while. And that's why I kept going for a bit. But we did have 620 a while ago, and if you're just narrowing things down, 620 and 680, you actually have 620 in hand, go with the 620, because you can't be guaranteed that there are some more. Still investigate up to your time limit, obviously. But yeah, that I did that one long, and I did that one too theory-wise, too much theory. I imagine we were supposed to just sort of make our charts and say, nope, that's it, we're done. I'd be curious to see if they had a faster or better way of doing it in the solution. I know sometimes when they write up a solution for a question where they're doing a whole bunch of chart stuff, and this doesn't usually happen for a 25, but it's usually for an earlier question, which is the whole bunch of chart stuff, they say, yeah, and you couldn't fill out this chart anymore. And okay, it's a multiple choice contest, but they wouldn't be pulling that sort of nonsense on a Euclid where you actually have to prove what you're doing. But 620, there's our answer, and that finishes off the Cayley. And yeah. So I'm going to start another math contest in a little bit. I'm going to go take a little bit of a break because this took me a while. But yeah, thanks for watching, and I will see you guys for more math videos in the future.